Hello and welcome to this lecture on LTE Radio Primer. In this lecture we'll be covering the main aspects of the radio interface between the mobile and the base station. So we'll be talking about the base station communicating with a bunch of mobiles out in the field, and we'll be talking both about how the base station communicates to these mobiles in the downlink direction and how these mobiles communicate back to the base station in the uplink direction. And we will, to cover all of this radio interface in one lecture is a tall order, so we will not go into the details. We'll try to provide you sufficient information to make you dangerous and give you the basics so that you can go and look at the next level of details from the specifications and other books out there. What we'll cover will be divided into two parts. In the first part, we'll be talking about the downlink direction, that's from the base station to the mobiles, and then in the second part, in the uplink direction. So in the downlink direction, we'll talk about the multiplexing scheme, which is called OFDM, and which is the way in which the base station sends data to multiple UEs. That's the multiplexing scheme. We'll talk about the downlink radio frame structure, what it looks like, and then also in each subframe how the mobile knows where to look for data. Concepts of logical channel and physical channels, the radio protocol stack, and also about measurements of the signal strength, which is an important part, especially used during handovers. In the uplink, again, we'll talk about the multiple access part of it, because here there are multiple UEs that are having to communicate with a base station. So that part of it is called multiple access, and we'll find out that it isn't OFDM, it's something called single carrier frequency division multiple access, and we'll provide a brief overview of that. The uplink radio frame structure, which is very similar to the downlink. Some aspects about radio frame synchronization, which is there in the uplink direction because the mobiles are at different distances from the base station, and all their frames coming up to the base station should be synchronized with each other so that they don't interfere with each other. And that part is dealt with the base station providing timing advance to the mobiles. The physical and logical channels, which are simpler than the downlink, and the uplink reference frame signals, which the mobile needs to send to the base station, which are different from the way they are sent in the downlink. We will not be covering details of MIMO or any physical layer details, so if you're interested in those things, unfortunately, they will not be covered in this lecture. So let's look at least at the highest level, when does a base station talk to mobiles, and when the mobiles are allowed to talk to the base station. And it's not just when. If you look at it at the end, it turns out it's a when and where. In the communication field, the axis of the domain that we are looking at is the time and frequency domain. The FCC, or the regulatory body, gives you a bunch of frequencies, and then you have time, and these are your resources. So how do you go ahead and divide your resources between the downlink and the uplink? There are two basic schemes in which you're aware about. One is that, okay, I'll split this time frequency domain into along the frequency axis, and in the top frequency part of it, the base station speaks to the mobile, and in the bottom frequency part of it, the mobile speaks to the base station, and they're both speaking at the same time. So this is called frequency division multiplexing or frequency division duplexing, because there are two parties only involved. At the general, this is the base station and the mobiles. The other way to split the time frequency domain is to split it along the time axis and say that, okay, in the first part of a frame, which keeps repeating, what I do is, in the first part of the frame, it is the base station that is talking to the mobiles, and in the second part of the frame, it is the mobiles that are talking to the base station. And I do the same thing in the next time frame again, and split it into two, and this is called this part of it is called it's called time division multiplexing or time division duplexing. So LTE supports both frequency division duplexing and time division duplexing, depending upon the country where you are in. Most of Europe has has frequency division duplexing, but China and India have time division duplexing. Uh, we will be focusing on our lectures on the frequency division duplexing part of it. We will not look into the time division duplexing, but a lot of the concepts carry over. Some of the details are different. The split is slightly different when you look at in deployment. Is that it is not the frequency provided for the downlink direction is separated from the frequency provided in the uplink direction, and this separation is there such that there is no leakage of information from of information from the downlink and the uplink. If you're listening at right the very next band in which you are transmitting for the mobiles, if the mobile is going to be listening for downlink right next in the bandwidth to where it is transmitting up, there is a lot of interference that would be happening, and you don't want that kind of interference. And so the uplink and the downlink bands are separated by some interband frequencies, and you end up in LTE with the maximum, as we had covered in the previous lectures, of 20 megahertz in the downlink, and you have a paired spectrum 20 megahertz in the uplink. The uplink is always at a lower frequency than the downlink, and you can think about it and see why it is. It's a pretty simple explanation. So now going into, let's at least cover what OFDM is at a very basic level, so that you have some understanding of this multiplexing scheme which is used, and which is the key scheme being used in LTE and also in a lot of the Wi-Fi and the WiMAX standards. So what does OFDM really stand for? Of course, we kind of know it's orthogonal frequency division multiplexing. But when we let's try to cover the first part of it, which is this orthogonal part. What does orthogonal mean? And what are orthogonal functions? So if you pick up Wikipedia and you look in there and you see, if you're having two time domain functions h1 and h2 of t, and you say that they're orthogonal over an interval of 0 to t, if their inner product, which is denoted like this, and which is an integral of the multiplication of the two time functions over this domain, is equal to 0. So you have a particular time domain t, time period t, and then you have these two functions, which is one is h1, and then you have the other function which is h2. So, and if you basically multiply these two and you integrate from 0 to t, the integral of the multiplication of h1 and h2 should be equal to 0. And this is denoted by, in this notation, which is also called the inner product. If you have a set of these functions, h1, h2, all the way up to hn, and you say that they are mutually orthogonal, you just extend that definition of two functions to a general set of functions, and you say that it's going to be equal to 0 if I is not equal to k. Otherwise, if the function is multiplied by itself, what comes out is what's called the energy in the signal. And if mi, which is the energy in the ith signal, is equal to 1, then we say that this function hi is not just orthogonal, but it is orthonormal. So orthonormal, which means these functions are not only orthogonal to each other, but their energy in each of these functions is equal to 1. And that is a good simplification, because it allows you to kind of try to figure out if a particular signal is present or not by just normalizing that signal by the energy that it has. So you can create an orthonormal set of functions from an orthogonal one by just dividing that function by the square root of the energy that's there in that signal. The important corollary that comes out of this is that, and this is what actually OFDM is ending up doing, is that if you have a composite signal where the signal consists of the various orthogonal or orthonormal functions multiplied by some scalar alpha I to it. And if you have this composite, if you construct this composite signal of all these orthogonal functions, and if you just take the inner product of this composite signal which with any of the individual orthonormal function, you'll end up with what is the energy of that particular component, the ith component in the composite signal. So alpha I times mi, let's assume mi is equal to 1. So you create a composite signal which, by summing up the various components weighted by some factor, and then in order to find out whether a particular component, let's say H2, is in this signal or not, you just take the inner product of it, and what you'll end up getting is alpha 2, and if your signal, if alpha 2 is not equal to 0, then you do have this component, otherwise you don't have this component. So in one way, this is also a very simple way of finding out whether a particular component is present in the signal. And that is exactly what OFDM is doing. OFDM takes a bunch of orthogonal functions, puts information onto them. So if you want to transmit a 0 bit, you put so if you want to transmit a 1 bit, you put alpha n is equal to 1. If you want to transmit a 0 bit in that same signal, you put alpha n is equal to -1, and you take these n of these components, you get n bits in there, and in order to decode these n bits, you just multiply them sequentially by all the individual orthogonal functions. And this equation, these two equations is a good summary of what OFDM is doing for you. And in the next slide, we will look at what is the orthonormal function that OFDM is actually using. And what OFDM is using for the orthonormal functions are cosine functions. So your h1 to hn are cosine functions. And there is a good property of the cosine functions that if you look at the harmonics or the multiples of a particular frequency f0, they are orthogonal over a time period 1 over f0. So let's take a simple example, and we'll take 15 kilohertz, and this is not just by accident, but this is also the base frequency of each subcarrier in OFDM used for LTE. So you take 15 kilohertz. The time period of a 15 kilohertz signal is, if you take 1 over 15 kilohertz, is 66.67 seconds. And you consider this as your base harmonic that you're sending. The reason we have taken a square root of 2 is that what we have done is that the energy in this signal is equal to 1 if this is a square root of 2. Otherwise, the energy, if you take the amplitude to 1, the energy comes out to be 0.5, and we just wanted to kind of normalize it. So we are using this factor square root of 2 to try to get the energy in this in each component equal to 1, normalizing it. And the second harmonic of this function will be h2, which has got two of these cosine curves within the 66.67 microseconds, go through h3, which is the third harmonic. Like this, you have the 12th harmonic, and what you do is, in order to send 12 bits of information using these 12 harmonics, each one of these bits you either multiply by 1 or -1 if you want to send a 1 or if you want to send a 0, and then you sum up these signals, and what you get will be the composite signal G. Over here we do it slightly differently, just to illustrate that that you can find out what the energy in the H1 component is. Instead of having 1 and -1 for the H1 component, we took the multiplication factor alpha 1 to be equal to 1 minus 1.5, and for all the others these are random, either a +1 or a -1 for all these other subsequent 11 harmonics, and we summed it up. And when we summed it up for in MATLAB, we just did a simple function. You'll end up seeing that your GT function looks something like this. The interesting part of this is that what you will see, and this becomes even, we'll talk about it a little bit more later on, is that this signal has pretty high peaks, and the average value of this signal is not very high. So this signal, OFDM signal, one of the characteristic is that it has a very high peak to average ratio, which is also called PAR. Peak to average ratios is pretty high, and which we'll cover a little bit later on what the ramifications of that are. But you end up getting a function which is GT, which we plotted that out. Now, in order to find out whether we do have this H1 component in this composite function G or not, and what the value, how we have weighted it, we simply take G and we get the inner product of G with H1. First, we just plot the time multiplication, the point-to-point time multiplication of GT into H1 of T, and it doesn't give you any information just by looking at it what you're getting. But when you integrate this function over 0 to t, what you get is a number, and that number is minus 1.5, and lo and behold, this minus 1.5 is what we had weighted the harmonic by. And so in this way, by providing different weights to it, we can put different information into here. So if you're doing something like amplitude modulation, where you're putting different amplitude of signals into a component, you can do amplitude modulation on this particular harmonic. So this is the basis of OFDM. And we will now kind of look at it in a little bit more detail, one more level of detail. And as we said, we kind of look at the time frequency domain. So we have time on the x-axis and frequency on the y-axis, and the frequency is in kilohertz. So we have a 15 kilohertz, as we said. The subcarrier frequency in LTE is multiples of 15 kilohertz, and that's how the design was chosen. To have a base frequency of 15, the 15 kilohertz. And we will look at this 15 kilohertz signals and its harmonics over time period of the base time period of this harmonic, which is 66.67 seconds. And as we said, this 15 kilohertz signal that when shown in the time frequency domain as a single line, in the time domain is essentially one cycle of this cosine curve. If you have 30 kilohertz, you have got 2 cycles of the cosine. 45, you've got 3 of them, and so on till you essentially get to the 180. And we'll at the moment kind of restrict ourselves to 180 kilohertz, and then on each one of these, assume that you're doing some kind of a 1-bit encoding, which also can be called BPSK. So when you have a 0, you multiply the signal with -1, and when you have a bit 1, you multiply the signal with 1. And if you do that kind and you generate random 0, 1 for all 12 of these, you'll get a signal which looks something like this for a particular combination of 0, 1 bits over here. And you send essentially this signal out in this particular period over here, and this is called an OFDM symbol. So this is your OFDM symbol, which is what you're sending over in the 66.67 microseconds, and it consists of 12 harmonics over here. Now what you can do is you can before we kind of go a little bit more detail into how this information is sent, or let's just kind of consider how we would send a set of bits over here. So if you've got BPSK, we can send one bit in this 15 kilohertz. If I'm doing something with a slightly higher modulation like QPSK, which is quadrature phase shift keying, which is putting 2 bits of information. So on this 45 kilohertz, I can have 2 bits of information, and on another frequency over here, 60 kilohertz, if I'm doing higher modulation, I can have 4 bits, which is my 16 QAM, and so on and so forth. So the way the information that is being sent is actually in this particular frequency over here, and in this particular frequency over here, that at the 30 kilohertz, and then at 45 kilohertz. So you're sending 1 bit or 2 bits of information, and the way it gets represented in LTE is that what they say is that this particular thing over here, this box, is called a resource element. So this is called a resource element, and it can carry either 1 bit, or it can carry 2 bits, or it can carry 4 bits, or it can carry 6 bits. 6 bits is 64 QAM, is kind of the highest modulation up to release 10, and then beyond release 10 they've gone into even higher modulation. So each of these resource elements that you have over here can be carrying 2 bits, 4 bits, or 6 bits. Of course, they kind of show it as if it's in this resource element. The main information is in the frequency that you are kind of transmitting. So it's in this frequency that you're putting in the 0 or 1 bit. All right. One thing that is also you'll see in quite a few books, and maybe a good idea to kind of at least look at the basics, is that instead of looking at the time domain, where we did look at the time domain, it becomes a little bit difficult to find out that there are multiple orthogonal functions just by looking at the time domain signal. But when you go into the frequency domain, it becomes a little bit simpler. And so now what in the frequency domain I'm plotting is a curve of the frequency spectrum versus the frequency. And if you have a 15 kilohertz signal, if this signal went on till infinity, you would have essentially just a kind of a delta function at 15 kilohertz. But since the signal is not going on till infinity, and what we have is a signal that is essentially just kind of truncated at time t, which is a multiplication of a signal that goes on to infinity with a t sample, with a t curve, which is a value 1.4 all the way up to 66.67, and then goes on to 0 till infinity. We know that, or at least if you've done some kind of communication, the Fourier transform of this kind of a t curve is as a sinc function, which goes down to 0 at 15 kilohertz from the peak on both the sides, and it's a convolution, so you end up kind of getting a sinc function which is centered at the 15 kilohertz signal. And essentially, if you take the Fourier transform of your 30 kilohertz, you'll get the same thing, but centered now at 30 kilohertz, a sinc function that goes on in the frequency domain to infinity, but centered at 30, and so on. And then for the 645 kilohertz, you get something like this. Now, when you add these things up, and I'm just showing 3 of them and not all 12 of them because it would take too much space over here. The important thing to see over here is that when the 15 kilohertz signal is at the peak, all the other components that are being transmitted, they have a value 0 over here. So that is why I can put in any information onto this 15 kilohertz signal, and whatever other information coming from these other harmonics, these 30 kilohertz and 45 kilohertz, they do not interfere with this information that I put in. So on the frequency domain, it becomes a lot easier to find out that these signals are actually orthogonal to each other, and I can put in information into each one of these, and they will not interfere. And I can decode it at the end very easily, because the other frequency components have zero contribution at the peak when a particular component is at its peak. So that's one intuitive way or intuitive feel of these functions being orthogonal to each other, but looking at in the frequency domain. A lot of times you kind of change domains to get a better intuitive feel of the problem. So, so coming back now to the time domain, which is always a little bit easier for us to understand. So we had kind of taken the time domain for one OFDM symbol. So we can repeat this to the next symbol, which is 0 to 2t, and we can keep repeating this. But before continuing to repeat this, one of the issues that that comes up in communication is time delay. So if you have a base station and if you have a mobile which is out there, when this base station transmits to the mobile, there are a lot of buildings and other objects which reflect the signal. So what you end up getting is you end up getting a direct path, and you also end up getting what's a time delay path coming to the mobile. And if there are two signals that this base station is sending to the mobile, and let's say that these are spaced at time t, and this is the first symbol is over time 0 to t, and the next one is over 0 to 2t. And let's assume that the first symbol had this, and then your next symbol that you're sending has another curve like these. And then when you send these over and the mobile receives these signals with a particular delay, this is now the delay, and here is the delay between these two. So let this be tau 1. So here you have a delay from the time that it sent to tau 1, and you essentially have things between t 0 to t is the first symbol, and between t to 2t is the second symbol. And the first symbol essentially has this OFDM thing that you had sent in 0 to t, and the next one has a delayed over here. But what's also happening, we said that there is another path, that is this path, that is the delayed path that is reaching the mobile. And let's say that delay, the time delay for the signal to go from this base station to the mobile is tau 2, and the delay between these two, the delay differential, is tau 2 minus tau 1, which is equal to delta tau. So what's going to happen is that a delayed version of the very first symbol will be received at the mobile also. And let me just draw this delayed signal starting at t3 at tau 2 over here, and this is at tau 2 from here. So there is a delay of delta tau. So what you will see over here is that for this period of delta tau over here, you have something called inter-symbol interference. Your previous symbol is interfering with your next symbol. So, and this interference becomes very difficult to remove in communications. So in order to kind of not have this kind of inter-symbol interference, and where your previous symbol clobbers the beginning of your next symbol, what is done in most communication systems is, of course, the most intuitive thing that you would do is that, okay, you have, instead of starting your next symbol exactly after the first the symbol is getting over, you provide an additional delta time between this to take into account for the worst case phase difference. And then you kind of go from here to you kind of have delta, and now you have t. So over here you essentially have delta plus t, and you would have done the same thing over here. So you would have started in order to I mean, of course, you start off from your previous signal. So this becomes tau plus, so t plus delta. This is 2 times t plus delta, and so on and so forth. And what you do in this tau period is interesting. What's done in LTE is, for example, we have the previous signal that we were sending. So we have this first symbol which we have sent over here, and now in the next period we kind of had this next symbol that we had sent over here. Now what they do is that they take this last part of this symbol and they copy, let me draw it with a black ink over here. So they take this last part of the symbol over here and they copy it onto the part which was being sent as blank, so that you don't have a blank over here. You end up having some signal so that you don't have some discontinuity. So this kind of reduces the discontinuity. One of the things that we see if we are doing this kind of a scheme is that even if this signal over here, this red signal, gets delayed by delta t over here, it will only clobber the initial part of the next symbol, which is also called the preamble. So when you keep a space between the first symbol and the next symbol, and you provide some buffer space between that, and you put in some signal over there, obviously to kind of try to remove the discontinuities, and also there is some other math involved in it, is that part of the signal that you're adding in here is called preamble. In LTE, the preamble is allowed to be 5 microseconds, which is actually a pretty big number for most communication systems. If you look at the speed of light is 3 into 10 raised to the power 8 meters per second. So if you have got essentially in 1 microseconds, you're going 300 meters. So in 3 microseconds, you're doing 1 kilometer, approximately 1 kilometer. So in LTE, the kind of time delay that is allowed delta, the distance, the time distance, which is also allowed with this 5 microsecond delay, is your reflected curve, your reflected wave can have a path difference of 1.5 kilometers compared to your main path, and that is fairly significant and allows you to have allows you to avoid intersymbol interference. And this 5 microseconds is still a small number. It's less than 10% compared to the symbol period, which was 66.67. So in the practical system, these symbols are not 66.67 seconds long. They are approximately 71 microseconds, 71 microseconds long, and you then essentially kind of send these symbols with a 5. Of course, you're sending with a 5 microseconds preambles provided in here, and you're transmitting these signals. It also comes out to be an interesting math that if you do 71 microseconds and you have 14 of them, you end up with something which is very close to 1 millisecond. And this 1 millisecond, 14 OFDM symbols in the time domain constitute what is a subframe in LTE. And this subframe is an important concept in creating the overall LTE signals. You essentially take this 1 millisecond subframe and you keep repeating this in time till eternity, and you will get an LTE downlink frame going on till eternity. Also, the important thing is that we consider 12 harmonics from 15 kilohertz to 80 kilohertz. This 12 harmonics together with 7 OFDM symbols is what's called a resource block. So this is called a resource block in LTE, which is nothing but 12 harmonics and 7 OFDM symbols. So if you look at it, there are 7 times 12 or 84 resource elements in there. So each of this is a resource element, and each resource element can have 2, 4, or 6 bits. So you can do your math and figure out how many bits can be sent in here. And if you have, of course, the minimum bandwidth in LTE is not 180 kilohertz, is 1.4 megahertz. So what you do is you essentially take this resource block and you multiply it in the frequency domain to fill up your frequency band over here, and then you repeat this in the time domain till you kind of go to infinity in time domain. I mean, for as long as you have, and that is essentially your radio frame that you get. So also to talk about how various bit streams are sent. Of course, with OFDM, what you could have done, and theoretically what is possible, is that you could be sending this 15 kilohertz to UE1, and you could be sending this 30 kilohertz to UE2. So you can be sending the bits of information in each frame, or actually even in this frame, to UE1, and then in another subfrequency band to UE1, and then to UE2 you could be sending it over here, and you could be sending it over there. So you could do this really arbitrary on a very fine subcarrier basis, but that is coordinating this with the mobile is much more complicated. And what essentially is done practically in LTE is that this one subframe is allocated to one UE. So UE1 gets most of the usable resource elements, and this subframe gets provided to UE1, and in the next subframe of, again, 1 millisecond, you will provide this to UE2. And in the frequency domain, what you will also do is you can provide this resource block which you have over here, these 2 resource blocks, to UE3. So this is the kind of multiplexing schemes that is used in the downlink direction. So all these resource elements have been provided to UE1, and all these resource elements have been provided to UE2. And in the frequency domain, of course, in the frequency domain, you can keep going for as many resource blocks that you have and you kind of allocate resource blocks in a subframe domain to different mobiles. And this 1 millisecond is also an important parameter, and which is called the transmission time index, the TTI. So this is the minimum time over which scheduling gets done. So you can change scheduling decisions every 1 milliseconds, and that is how fast you can decide who's going to get resources in the time domain, and that parameter is the transmission time index. So quite a few concepts that we have kind of covered in this one slide, but that kind of provides you the basis of OFDM. Let's just kind of quickly cover how the OFDM signal is generated. In the previous figure, we had said that this entire resource block is provided to one UE. So if you've got a bunch of, let's assume that you're doing QPSK, and you're providing 2 bits in each of these carriers. So you've got 24 bits of information that you have, 0, 1, 1, 0, 1, 1, like this. So you've got 24 bits over here. You take these 24 bits and you provide the first bits to the 15 kilohertz, the next 2 bits to the 30 kilohertz, the next bits to the 45 kilohertz, and so on. So you essentially take this serial 0, 1 bits of 24 bits, and you put them into a parallel structure over here, and then with 2 bits into each of these frequencies, you multiply it by the frequency, you add the frequency, and you send this OFDM symbol. So that's what you are doing for each mobile